In this video, we'll move into section 1.8 and start discussing our next major topic, which is the idea of continuity. And the book, I really think, once again, does a very good job going through this topic. I'm just going to say I go through these ideas in a slightly different order so that way we can kind of get all the big picture. You already see I've got a big graph here that we're going to use to get a lot of our basic ideas started. We're going to start with a visualization of what the idea of continuity is actually telling us about a function, and then we'll move into the definition and start to get into more of the equations. So, you go back to the very beginning, we're still going to have to deal with both graphs and equations, and just like we saw with limits, just a basic understanding of the concept, and we can answer all questions based on the graph. But then we need something a little more formal. We need a more formal definition. For the limits, we needed some extra limit rules that were based on the definitions in order to proceed with the equations, and very similarly, things are going to happen like that here. So, first thing, an informal idea. The idea of a function being continuous. My function f of x is continuous where its graph is connected. That is the synonym that we want to establish. That when we understand the idea of continuity, that there's this aspect of connection, that its graph is connected. So when we start talking about where the graph is connected, we often start by identifying where it is not connected. And we have a special term for that. We refer to those points as discontinuities. The discontinuities are where the graph is not connected or disconnected. So we're getting that very, very quick, close association between the words of connected and continuity. So not to repeat too much, but the idea of limits, we had to talk about approaching both sides. As we approach that x value, what does the y approach? And then we got a lot more formality from it. And that was enough to get through the graphs. And similarly, this is all we need to get through the graphs with the idea of continuity. Discontinuities, where the graph is disconnected, not connected. Now, one tiny little thing to say with this. When we talk about these discontinuities, we're only referring to individual x's, little blank spots. So just quickly on the side here, I'm going to draw the graph of the square root of x. That would be y equals the square root of x. Just this little hook that comes out of the origin. There is no graph over here on the negative side of the x-axis. This function, its domain does not allow for negatives. You can't take a square root of a negative number, so those x values are not in the domain. But we don't talk about any disconnected over here because there's no graph. So again, when we think about discontinuities, looking at this big graph I have here, we're looking at the individual x's. So that all this over here, all this piece of graph, the idea of connected is that I can draw it with my pen or pencil without actually picking that utensil up. So I could do all that in one motion. So all of this is connected. But then I had to pick my pen up to jump across this asymptote. So this x coordinate, this asymptote, would be our first discontinuity. But then as I start on the other side of the asymptote, all of this is connected. But then I had to pick up my pen again to move down here. And at that x coordinate, that is another discontinuity. Similar when I get over to here. All of this, another piece that's connected. Now right here, this is just a tiny little open hole, but it's still a disconnection. It doesn't matter that I'm disconnected because I'm jumping across an asymptote, or I'm making this big jump from being up here to down here with my graph, or right here, just this tiny little open space. And similar over here, this little open space has a filled in point at the x coordinate. This one does not, but all that doesn't matter. This little open space disconnects this region of the graph from this region. This little open space disconnects this region from this region. And then we still have one more discontinuity right here. as I jump, going up on this side of the vertical asymptote to being down here on the bottom, but doesn't matter that I'm going from the top of the asymptote to the bottom or back over here where we're both at the top on both the left and the right, it's still not connected. So all of those are discontinuities. The next big thing I want to focus on, which I kind of already mentioned, is the second aspect. We are always going to be interested in where. The questions are always going to be, where are the discontinuities? Where is the function continuous? So that idea of where, we get to really take advantage that we will always be dealing with functions. So when you're dealing with a function, just a quick reminder, the whole idea is that every x only has one y. And the big advantage that gives us is that now the where, we can always identify where things happen based on the x. So we're already very quickly, just through this basic quick definition, we're already very quickly moving through our first problem. I haven't even given you any directions, but we're already getting so many of the ideas. So let me spell it out. So our first problem here, you are given this graph of f of x, lots of weird stuff happening here. And my first question, number one, where are the discontinuities of f of x? Sometimes the book says find the discontinuities. Where are the discontinuities? The same question. I definitely want to focus on where for right now to make that very clear. Where is always an X question in calculus. Okay? So where are the discontinuities? Well, I go back and I look at my graph. And again, especially for a lot of people in the beginning, it really doesn't hurt at all to trace over the graph. Like, okay, all this is connected, picked up my pen. Where did you pick up your pen? At this x value. So that x value, x equals -2, that is my first location where I have a discontinuity. And then I could pick it up. Now I realize some of you can just, do this a little bit faster, and that's fine. Especially with a little practice, we're just looking for the breaks, the jumps, the holes. Those are the discontinuities. But to be very thorough in this first one, now I'm retracing. Again, had to pick up my pen. Had to pick up my pen to go from here to here. So this x coordinate, that'll be x equals -1, will be another discontinuity. And now I'm continuing. So starting from here, up, had to pick up my pen to make this circle, right? I could try, this is where some people can say, well, I can keep my pen down, make the circle, loop back around and keep going. You could try and stretch what I'm telling you here and say that's not, but that's missing the idea. Because remember, this open circle, that's something we use to help visualize what is happening. But really, all that's happening, let me do this off on the side, is that. That's all that we have. A point is so tiny by itself that if we don't draw these big circles like this to really emphasize, you wouldn't even be able to tell. Maybe if you look super carefully and zoom in, you could see I left a tiny little gap right about there, right between those two little segments. But that's the reality of graphs. And when I do that, I had to pick up my pen to make this line and then make the second line without them touching. So again, that little open circle, that leads to another discontinuity. That happens here at this value, and that is an x value of 1. Notice, everybody, again, you can only answer these by x. The book sometimes says find the discontinuities, and there are other problems when they say find what they're looking for, and if they say find a point, well, they assume you're going to give them the xy pair. But notice, you can't give xy pairs for any of these. You can't say it's discontinuous at an xy pair over here because there is no y. How does that make any sense? The only information that helps is the x because there is no y to go with that. Similarly over here. Now some people would argue, well, at least this is an xy pair. -1 comma -2 is a point on this graph. But that's not the discontinuity. The discontinuity is that you're making the jump from here to here. So just because this is filled in, that has no bearing and doesn't help anything at all with the regard to the discontinuity. So again, that's why you can only give the x. Same thing here. You want to describe the discontinuity. Well, now some people feel a little more comfortable describing it as 1 comma -2, because clearly that's the open circle where we're making the break, unlike here where we've got this whole big jump. But again, doesn't matter the different circumstances, they're all discontinuities. So again, we always just use the x to describe where it happens. So let's finish. We still have 2 more here. That was a discontinuity. That was x equals 1. There is another discontinuity. That is at x equals 3. And then one more discontinuity over here. And that is x equals 4. Now, this is only one problem. We'll do a follow-up with this in just a minute. But just to realize, don't try and make too much out of one example. Some people see this problem and now they're always looking for 5 discontinuities. Every problem is individual. Some functions, they don't have any discontinuities. There are no breaks and jumps. Other graphs have lots, have an infinite number. Other graphs just have a couple, 1, 2, 3. So again, each problem we have to handle individually. We want to make sure we're understanding the concept and not just trying to memorize something that's not there. Okay, so we've got the discontinuities, and now that allows me to move very nicely into our next question. Where is my function continuous? We can talk about all the places where the graph, all the points of continuity, but unlike up here, the discontinuities, where we have a handful. 5 is still kind of a bunch, but that's still only a handful in the grand scheme of things. But when you think about continuity, well, where is the graph connected? So let me go back up here. Well, the graph is connected here. The graph is connected here. The graph is connected here. Here, 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 here. Here, 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 here. All of these points, the graph is connected. So it's impossible for me to label all the x values the same way I labeled all the x coordinates where we had discontinuities. Here we need something a little better, because we're going to realize we're not just connected at an individual point or two. We are connected over entire intervals. We are connected for entire durations. So we're still answering a where question. The answer is still an x. But now, starting to understand the context. Discontinuities happen at individual x coordinates, so that's how they will be labeled. The continuous regions, we should assume it's going to be for large, doesn't have to be super large, but for intervals. So we'll expect interval notation here. Now, some people can very easily just look and say, well, where is this connected? As soon as I get on my graph, so as soon as I jump on, that's -infinity, right? I'm coming on from the forever from the left. So I'm starting continuous at -infinity, and I'm continuous for all these x coordinates because this is all connected. And then it's discontinuous here. So I'm continuous for all these values up to and not including -2. So my first region of being continuous would start at -infinity. Remember, infinity, positive or negative, is a concept, not a real number, so that always gets the parenthesis. You can't actually get there. You can't get to or reach infinity to actually include it, so it always gets the parenthesis. And then we have our discontinuity at -2, so that also gets a parenthesis. It's continuous everywhere before -2, but then right at -2, it's not continuous. It's discontinuous. Okay, and now I pick up on the other side, And now I get a smaller region, but this is still all continuous. And even though this region is smaller than this one, there's still an infinite number of x's. It's easy to say, well, I'm just between -2 and -1, but still the fractions and decimals in between, there's still an infinite number. So some people, again, just looking on the x-axis, they can just see that. And now I want to give you the next little tidbit. For a lot of people, even if this question is not asked, even if you're not asked for the discontinuities, most people do this part first anyway. Because for most people, the easy way to figure out where the function is continuous is to start by saying, where is the function discontinuous? And then say, okay, it's continuous everywhere else. So I'm going to come up here. I'm going to say that again and just show you using these x coordinates, but I also want to come up and get a full picture of the graph one more time and point out how a lot of people go, okay, the graph is discontinuous. Let me change my pen color. So the graph is discontinuous here, 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 and here. Those 5 red x's correspond with the 5 x values we identified for the discontinuities. And then we don't have any other domain problems. So we don't have this issue I was mentioning here. The function is defined everywhere else, and everywhere else is where it is continuous. Looking on the x-axis, it's continuous for all of these x's, and that is this first interval. Forever to the left, up to not including this point, that is the -infinity to -2. Then I'm continuous between these two. So that will give me the interval that's -2 to -1. Quick reminder, when you have multiple intervals, the union symbol is what's appropriate. I don't mind if you don't include it. I do need the intervals. Okay, I need to see the interval notation. But if you just put a comma in between or just list them, that's fine. Just like even up here. You need to at least identify this is an x equals, but then you don't have to keep doing x equals. You could just list all these x values and put a comma in between. That's fine, okay? So now let's keep going. So back up here. Now, discontinuity, discontinuity, continuous in between, and that gives me the interval -1 to +1. Keep going. Between here and here, discontinuity, discontinuity, but all this in between is connected. So we've got another region of continuous from, 1 to 3. Still 2 more, because now we're back up here. Between these two, another short little interval, but still all of this is connected. So that is 3 to 4. And last one, not to forget, it's easy to forget this one sometimes, everybody. But now, just to remember, all the rest of this is continuous forever. Our graphs, we don't put arrows on these, but we assume they continue with that trajectory. This is kind of flattening off this way, same way this was flattening off over here. Sometimes they shoot up or shoot down forever, but it's still kind of continuous in this pattern. So all of this would still be continuous. So we're continuous from 4 to +infinity. 2 more things I want to say before we move past here. Okay, I still want to I realize for some of you, you've got the idea, that is fantastic, but I still want all of you to realize the little different ways that people see this and proceed. But no matter what, we're looking at the graph, we understand the concept, both of these are fairly quick questions. That even if there's a bunch of x discontinuities, well then that leads to a whole bunch of intervals where it is continuous. But as long as we have the idea, this is still a pretty quick problem to go through. So, 2 quick things before we move on. We'll do another one, get a little extra practice here, and then we'll get formally into the definition and start looking at the equations as well. So, first quick thing. Once people set up these discontinuities, do you notice how those set up all the intervals? We've got 5 discontinuities. Well, that breaks the x-axis into 6 intervals. I mean, some people like to draw it a second time separately, but I already have it on the x-axis right here. That's my number line, and maybe just because the red x's are starting to blend in with my scribble, I will highlight them a little more. Get rid of this, get rid of this, get rid of this, get rid of this, get rid of this. Just looking on a number line, that leaves us with 1, 2, 3, 4, 5, 6 sections that is left after you use these 5 x's to break it up. So those are the 6 intervals. And notice, you start at negative infinity, and then you end here, and then the next interval goes from here to here, and then the next interval goes from here to here. You're just going from one discontinuity to the next. Now, I started off pointing out why the infinities, in any context, the infinities always get parentheses. But now some people would look and say, well, wait a second. Why isn't this interval right here, why don't I have the bracket on the -1? The -1 is filled in with this interval, so why doesn't it get the bracket? To be continuous, it assumes you're, again, that idea of connected, and to be connected, you have to have a left and a right. So true, it's filled in here, but it's still not connected on its left side. It's connected once I get right past that point. So that's just a quick little lesson. If it's a discontinuity, it'll never be a bracket here. So in general, not in general, it will never ever be a bracket for a continuity question, because you always already have to start somewhere and then continuity comes after. So you can't start at infinity or negative infinity, but the continuity comes right after. And then whether you've got an asymptote or an open hole or whatever, but all these points are breaking up our graph so that you're continuous, not at that point, but it's got to be right after that point. So again, I hope that helps a little bit, just a few little different ways. And the last thing I want to say before we move on is, even though both of these are fair questions, and I still have one more thing, before we do a second problem, there's one more tiny little aspect to add to discontinuities. We have a classification that we want to add to them. But just before we do that, just to point out that a lot of people, again, these ideas definitely go hand in hand together, but a lot of people see the differences, the discontinuities, you're just focusing on the breaks and holes. So they could just answer this, and if that's the only question, they're fine. And if the question is about continuity, well, again, they may have to do this, or maybe they just look and just see the regions where it is connected. So a few tiny little variations, but all pretty much leading to the same idea. Okay, so still going to use this graph for one more, because now we have to take one more moment focusing on discontinuities. And that when we look at our discontinuities, they are classified into 2 different categories. Oops, make sure I'm on page. So discontinuities are classified as either removable, a removable discontinuity, or a non-removable. The idea of a removable discontinuity is that I'm being a little quick with my definition, I'm saying more. A discontinuity is removable if, by changing one point, you can fix the discontinuity. The key here is one point. That if you had the ability to change one point on the graph, does that fix the discontinuity? Does that fix the disconnection? And then non-removable is basically if you can't. If you can't fix the discontinuity by changing one point. So there's not too much here. And again, these are still all informal. We're going to finish this little exercise, do a whole separate one with the graph, and then I'll start a part 2 video where we'll start with a formal definition, revisit everything we've done so far, see why that works, and then we'll get into the equations and finish up this lesson. Okay, so removable, change one point, do you fix the problem? Do you fix the disconnection? Non-removable, change one point, you can't. So let me start off by actually showing you something that is removable. That is a removable discontinuity. It's just this tiny little one little point gap from this section of curve to this section of curve. So if you could, we're not going to change the function, but if you could pick up this point and drop it right here, now all of a sudden there's no gap from here to here. Now all of this would then be connected. So that x equals 1, this would be a removable discontinuity. So I'm going to add a little bit to part 1. We already did where are the discontinuities. Now I'm going to add classify each as removable or non-removable. And this would be removable. That again, if you could pick up this point and drop it in right here, I mean, if you pick up this point and put it up here, it doesn't help. It's the point, not just can you move it, it's if there's a place where you could move it and it fixes the disconnection. This point moves to here and it is connected. Okay? Come to x equals 3. That one is also removable. This one doesn't even have a point at x equals 3. If we just look at f of 3 here, we get it does not exist. There is no piece of graph that goes up and down from this point. All we get is this open hole. But this one is also removable because if I had a point, doesn't matter if there was one, here we had a point so I could pick it up and move it here. Here we don't. But if I did have a point and I plopped it right in that open hole, it fixes the disconnection the same way this did over here. So 3 is also a removable discontinuity. But what about the others? Well, let's come back over here. Some people have a misunderstanding on this one. Some people now, they're just looking for open holes. They see an open hole, they see an open hole, those are removable. They see an open hole, they go, oh, removable. I could fill in the open hole. It's like, yeah, that's true, but it's not just I could fill in the open hole in both of these. It's when I fill in the open hole, it connects the graph. If you fill this in, does it connect this piece of graph to this? No, it does not. It would take an entire line to connect this to this, and that's not allowable. It's only one single point. So sure, you could fill that in and make it a filled-in hole, and that's changing one point, but it doesn't fix the disconnection. So therefore, -1 is non-removable. And now what about the two asymptotes? Well, let's jump out to 4 first. Hopefully we realize 4 is definitely non-removable. There's no way you're filling in a point and connecting this to this. There's just no way to connect this to this by filling in a single point. So that one is definitely non-removable. But what about over here at x equals 2? -2, I'm sorry, at x equals -2. This is also non-removable. Now, some people, I don't want to mess up my picture, but some people be like, what do you mean? I can make a point. And they draw a big fat point, scribble it all in, and now these two sides of the graph connect. That's missing the point, everybody. Because a point, as we're describing over here, a point is tiny. A point by itself, in essence, takes up no space. So I need these open circles so we can clearly see that. But here is a point. That's a point. That point is not connecting that and that. So just scribbling a big fat circle, that's just not cutting it. Remember, everybody, the whole idea of an asymptote is this wall that separates whatever's happening on the left side to whatever's happening on the right. So one little point is not going to connect. Not that this should be what's memorized. The idea, I hope, is being established here. But some people do realize these asymptotes, they are always going to be non-removable discontinuities. Okay, everybody, so let's take a second look. Let's now look at a new quick function. I'm going to draw function g. And we're basically going to ask the same questions just to get a little bit more practice. So here is function g of x. And our function is going to do this. That is, oops, and one more, there we go. That is our whole function g. And we're going to hit the same two questions. Now I'm asking you all the questions here. If a test or a quiz question only asks about just the discontinuities, well then just do the discontinuities. If it just asks about continuous, well then just do the continuous part. I want you to see everything through this example, but make sure in the homework, any test quizzes, you're just doing, don't do extra, right? Just do what the question is asking of you. So number one, where are the discontinuities of G? And we will classify each as removable or non-removable. And then number two, where is G continuous? Just for short, everybody, because we're going to hear that term a lot, continuous. So I'm just going to start reading C-O-N-T, continuous. Okay, and now, again, you could take a moment, pause the video, go through, shouldn't take you too long, but now I'm going to jump right in. And again, if we're good understanding, these are quick questions. Where are the discontinuities? I'm disconnected here at this x, here at this x, here at this x. This function has three discontinuities. X equals -1, x equals +1, x equals +2. Removable, non-removable. Here, fill in the point, doesn't matter, that's not connecting. That is non-removable. 1, nothing you can do here. No point to connect these two regions. 1 is also non-removable. And now 2, that's the one. That's the one that if I just fill this in, now all of a sudden this does connect. So 2 is removable. Where is G continuous? Everywhere it is not discontinuous. Now, you can't, that's the idea, everybody. But again, I need the intervals. Don't just say x not equal to -1, 1, and 2. You should be able to give me the intervals that go with that. So what comes before -1? Negative infinity up to not including -1. Between -1 and 1, not including either because they're both the discontinuities. From 1 to 2, and then everywhere after 2, 2 to infinity. Okay, everybody, so again, that's part 1. In part 2, we'll discuss the formal limit definition and then start doing some equation examples based off of it.